So we discussed what is BFV at classical level, more or less understood. There are plenty of examples, of course, starting from spinless relativistic particle, and all possible spinning particles are objects of this type. We will have an example later already at quantum level. Of course, all gauge theories, when formulated in terms of Hamiltonian formalism, can be brought to this form as Hamiltonian system, but of course with infinite dimensional phase space. Now we switch to quantum level because that's what this approach was developed for, to quantize and to study quantum theories. And first I want to discuss the general aspect of what we call quantization. So let's briefly recall what we understand by quantization. So canonical quantization, let's think in terms of examples. So suppose we have a coordinate, momenta, and they satisfy the standard Poisson bracket relations. For simplicity, I just think that there is one coordinate, one moment, or you can imagine the index which is omitted here. So it's the simplest phase space you can imagine, and it corresponds to Hamiltonian dynamics, right? So this is classical level, and in general there is a Hamiltonian, which is a function of PQ and potentially time, which determines evolution in this phase space. Points of this phase space are states of our classical Hamiltonian system. Then we say, when we want to quantize, we want to construct a quantum system corresponding to this. What we usually say, we say, okay, fine, now our variables are promoted to operators, and these are subject to the following commutation relations, where there is a certain parameter. So what is important, that quantization of a classical system depends on a parameter, which is usually assumed to be a real number. But in general, there can be more tricky situations. For instance, h bar can be a formal parameter, or one can exclude certain values, like for instance, h equal to 0 does not belong to possible values, so you can only take limit, but we exclude all this. We discussed just this simple setup. So, and h is, well, if we say that it is in real numbers, it commutes with P and Q. So this fully defines associative algebra, right? So it's an associative algebra which is generated by Q, P, and in fact it's convenient to think that H is an independent generator which commutes with everything, and that we can always set it to a particular real number. And these relations and the fact that H is central. H is central, so commutes with everything. So this is usually the algebra which we work with, and this algebra is called a quantization of our classical system. So let's concentrate a little bit more on properties of this algebra, right? So first of all, it can be identified as a linear space, not as an algebra. It is isomorphic to algebra of, let me call it A, just functions of Q and P, with functions in H bar, right? So we write generic expression in Q, P, and H bar. H bar commutes with everything. So this means that it's a tensor product of a function in Q hat, P hat, and a function in H bar, right? So it's such an object. Of course, this isomorphism here means as a linear space. Not as an algebra.
What does H central mean?
Commutes with everything. If you want to think more algebraically, and when we do computation, sometimes it is convenient to think of H bar as an independent generator of our algebra, right? We can always set it to H equals something at the end of the day. But sometimes it's convenient to think of it as an independent generator, or if you want additional coordinate, if you really want it to be real, additional coordinate on our space.
Central extension.
Well, it's not really this thing. Maybe one can phrase, but it's not usually the language. I'm not sure if it's a good terminology. It's just standard canonical quantization. What I want to attract your attention to is that we are dealing with either, we can think of this algebra as an algebra generated by our phase space coordinates seen as operators, and of course now they don't commute any longer, and an additional element H bar, which is of course a Planck constant. Or alternatively, you can, in this algebra, we can always set H bar to a particular value, to a particular real number, and get, so let's put it, if we set H bar equal to H naught, this is going to be a particular associative algebra H naught. The question is that this algebra depends on the value of H naught, right? Because, for instance, look at relations of this algebra. Commutator of Q and P is proportional to H bar. This means that relations of our algebra are functions of Planck constant. So if we think of Planck constant as a parameter, it means that we are dealing with family. We are dealing with the family of associative algebras parameterized by a real number, which is a Planck constant. Why do we want not to set H bar to a particular value, but to keep it as a free parameter? Because we want to understand the relation between quantum system and the initial classical system. Sorry, before doing this, let me introduce one more notation here. So I want to introduce, we see that there is this isomorphism. Let's fix this isomorphism. So let's say that there is a map sigma which takes us from a tensor CH bar to U. And by sigma minus 1, I'll call its inverse. So this sigma is called quantization map. Quantization map. What it does, it takes possibly H bar dependent function of our phase space and gives us an element of our quantum algebra, or roughly speaking, an operator. And by sigma minus 1, I denote the inverse one, which is usually called symbol map. So what this isomorphism tells us? It tells us that we can parameterize our elements of our algebra, of our operator algebra, by elements of our classical algebra of functions, possibly dependent on H bar. That's what it means. And if we fix this map and we require it to be H bar linear, then we can identify operators. We can parameterize operators just by functions from A. And these functions are called symbols of these operators, right? That's what you all know when we have, for instance, we can decide about the rule. For instance, put all q to the left, all p to the right, and out of an expression, for instance, if you have a function, I don't know, qp, we can associate to it like q hat, p hat, right? Or and same for other functions. So this gives me this quantization map. So like this, for instance, I can write. Okay, what are properties of such a map? Properties of such a map is called correspondence principle. Correspondence principle, which tells us that if we have two elements f, g from our U, and if we multiply them as an elements in U, then apply sigma minus 1 map. So we get function, we get element from here, and then we set h bar to 0. We get just multiplication of the respective function. This is just sigma minus 1 of f h bar to 0, times sigma minus g at h bar equals 0. So if you multiply two operators, apply the symbol map to get respective functions, and then set h bar to 0, it's the same as to multiply the respective functions. So it means that quantum multiplication becomes just multiplication of functions, of phase space functions in the limit of h bar equals 0, right? And second, that the first order in h bar correction to the first order antisymmetric part in h bar is a Poisson bracket. That's we write like this. So if we compute commutator of fg, then we need to divide by ih bar. It's convenient. Then we apply sigma minus 1 and put h bar to 0. We get just a Poisson bracket of sigma minus 1 of f, sigma minus 1 of g. So this is called correspondence principle. So that operator multiplication to zeroth order in h bar is just a multiplication of phase space functions, and the quantum commutator to the linear in h bar term in quantum commutator is just a Poisson bracket. This does not uniquely define quantization, as you know, but it sufficiently restricts the class of what we can get. And often quantization is almost unique, not always, far from being always, but often it is unique up to natural equivalence if we start with a certain classical system and we apply this correspondence principle. So, and this is actually gives these properties, which we abstract from considering just a canonically conjugate coordinate and momenta, gives us a definition of what quantization is. It's a very subtle subject. In books you may find slightly different terminology, etc. And there are different versions of what quantization is. But this is a kind of compromise between the different ones. Okay, so definition. If we have classical mechanics, which means a Poisson bracket, it's Poisson algebra. Its quantization, its quantization means that U is, as we mentioned, is isomorphic to A tensor CH bar, and then this correspondence principle holds. So in addition, we require this. And then we say that this is quantization. Sometimes this condition is not fulfilled, then it's quite a special quantization. But it's not the one which we usually use when we speak about quantum mechanics. For very exotic systems, it can be that this isomorphism doesn't hold. For instance, if you heard of what's called fuzzy sphere, like if you know that, for instance, sphere S2 is a symplectic manifold. So there is a perfect algebra of functions on a sphere, is a Poisson algebra, and you can ask what is quantization. But if you ask for a good quantization which preserves symmetries, because we can rotate our sphere, right? It's a homogeneous space, then it turns out that you can only, and also if you ask for a representation in a Hilbert space, we will discuss this now, then it turns out that this doesn't exist. A quantization satisfying this doesn't exist, but a good one, which is physically correct, etc., is a different one where this isomorphism doesn't hold. Moreover, for quite often U happens to be a finite dimensional algebra. But this is quite a tricky setup which we don't discuss. Okay, in addition, if we want our quantum algebra of quantum operators to be represented in a Hilbert space, then we ask that there is a representation, so representation from, which means U to hom HH, right? So there is a map from our algebra to operators in our on our Hilbert space, and we want rho to be H linear. I think I should somewhere keep H bar here. Just a moment. I forgot a little bit. Just one moment. Let me make sure. Yeah, right. If you want to keep H bar as a parameter, we need the following. So we have C like this. So we want everything to depend on H bar, but if we set H bar to a particular value, then it becomes just a representation of our A, which is our U at particular value of H. Okay, good. Then what happens if we want to quantize a system which is our BFV system, which we discussed recent 2 lectures? First of all, we have a grading. We have an additional degree. So in this case, our A is a graded Poisson algebra. So it means that if we ask for its quantization, then we should assume that our algebra U is also graded. We denote the degree by the same symbol GOST. And this map, which identifies the symbol map, which identifies, or quantization map, it's inverse, this with this preserves the degree. So it means that sigma, which is a map from our A tensor CH bar to our U, and the degree of sigma is 0. And of course we assume that degree of H bar is 0, so that no miracles happen. Okay, and that multiplication U is an associative algebra. So if we multiply, so let's do it like this. GOST of Fg is the GOST of F plus GOST of G. So it means that multiplication in this algebra U is compatible with the degree. So it's a graded associative, Z-graded associative algebra, right? And once it is a Z-graded associative algebra, we can make a graded Lie algebra out of it. So we introduce graded commutator. So we say that by definition, Fg is just Fg minus 1. This formula remains correct even in the case if there is an additional Grassmann degree, because this is a total Grassmann degree, right? In case if there are no fermions, this, if no fermions, then F is just GOST degree of F modulo 2, right? So you see, if there is a graded, if there is an associative algebra, you can form in general different Lie algebras out of it, because you can either consider A as just a associative algebra or as a graded associative algebra if you have some additional degree, and then you can introduce graded or supercommutator. The difference is in this sign. And of course, for us, everything in this setup, in this world, everything is graded. So it means we, by commutator, we always mean graded commutator, so means with such a factor. Okay, and what about representations? So we want, if we have a representation of our U, so if there is this rho, then we want, of course, that the degree is preserved. So it means that rho doesn't change degree. But also our representation space in the graded setup is now naturally a graded space. And we still keep the convention that it is Z-graded. So it's a direct sum of homogeneous components. So our representation space, just like our space of functions on our phase space in the graded setup, where we have implicitly, it means that we have GOST somewhere, then our representation space also carries degree. So there are like states, elements of our representation space, these are quantum states, which are sitting in different degrees. And our assumption is that somehow we want our physical states to appear in H naught, in degree 0. This is not a standard convention. Sometimes when discussing BRST quantization of like particles and strings, people use different convention where physical states appear at degree 1/2. I will explain why it can be also convenient. It's purely question of, it's a question of conventions. But for some reasons, I believe it is most, for this general discussion, it's more systematic to assume that there is a distinguished degree, and let it be 0, where our physical states sit. That's what we want at the end of the day. But in the literature, there can be slightly different conventions, but the translation is straightforward. There is nothing deep in it. I will explain what the thing is. And why there is a freedom in how to parameterize these homogeneous components. This is because this is just a linear space. We don't have an algebra structure there. Look here, on our A, or after all, in our quantum algebra U, we have a Gauss degree, and we want this degree to be compatible with algebra structure. So if we multiply two elements, the degree of the product is the sum of the degree of the factors, right? So if we shift by 1 the degree of all elements of our algebra, this is not going to hold any longer. So it's not a graded algebra any longer. But in our Hilbert space, if in our representation space, if I shift by 1 the degree here, nothing changes, because all I want is that rho carries degree 0. What it means? It means that if I act with an element f on a vector, let's say phi from H, then I want the degree of this thing to be a degree of my element f plus the degree of my vector phi, right? I need to close it, it's too windy. That's what it means, that degree of my representation map is 0, right? You see that the degree of the result of acting of f on phi is just the sum of this degree. So rho doesn't bring its own degree. It means the degree of rho is 0. But you see, in both sides of this equality, we have just degree of degree in the, because it's a vector in our H. So if we shift it by 1 and shift it by 1 here, the equality stays. So it's a matter of convention where to set the where H naught is located, right? So we can always shift the degree such that our old H naught appears at certain different degree. But the agreement is to pick this degree in such a way that physical states appear in degree 0. This is just a convenient agreement. Some people do it differently. They assume that it in degree 1/2. Again, we can shift also by something which is not integer, but okay, I don't find it natural, but that's what people do sometimes, and I'll explain why. Okay, very good. But eventually, we are interested in quantizing BFV systems. But in the BFV systems, we have additional ingredients. So let's give a definition of what is quantum BFV system. A quantum BFV system. So it means that we have such an algebra U. We have a distinguished element omega. Now let's put hat on it. In U, we have a Hamiltonian, which is also element in U. Element in U, and we have our representation space. Representation space. And the quantum versions of our defining equations hold. So for omega, we have half omega is 0. gain ghost of omega is 1. And we also have that our Hamiltonian is BRST, let's also put hat on it, is also BRST invariant, and its Gauss degree is 0. So everything is the same. The only difference is that now our algebra is non-commutative, and there is a representation space on where it acts. And if in the classical limit, when we send h bar to 0, omega becomes our initial omega, and h hat, well, strictly speaking, sigma minus 1 of this, and sigma minus 1 of h hat at h bar equals 0 becomes our initial Hamiltonian. Then we say that this system is a quantization of the system with BRST charge omega and Hamiltonian h, right? And in this case also our u is a tensor with ch bar. Is it mine? Okay, so you see, here we start to see the advantage of working in terms of this BFV formalism, because we know how to define, how to take into account constraints and gauge invariance at quantum level. We just replace the classical master equation, which is the same where commutator is replaced with Poisson bracket. It's just its classical limit of this equation with this quantum equation. And the same for condition of BRST invariance of the Hamiltonian. So we know, because like this system is specially prepared, we know how to define its quantum version immediately. Why this is not so trivial? Because we can think in a naive way. Suppose we have a constraint system, right? So we have our constraints on our phase space, and suppose we quantized our phase space. It means that we arrived at some quantum constraints, and there is a Hilbert space. There is our Hilbert space where everything is represented. So what we want apparently to define the notion of a physical state. This is something like T alpha hat on acting on psi physical is 0, that it should be annihilated by the constraint. But the problem is that once we write this equation, we want to consider consistency. It immediately follows that this should also hold, right? I just act with T beta and anti-symmetrize in alpha beta, I get this equation, right? So this is consistency condition for this equation, which selects physical states for me. But the problem is that at classical level, we knew that Poisson bracket of T alpha with T beta is again proportional to T. But upon quantization, it can be spoiled by h bar corrections. So in general, what we know is that T hat alpha, T hat beta is of course something times T hat gamma plus h bar on something. And this h bar on something may spoil everything. Which means that apparently it's not clear if we can pick quantization in such a way that this term disappears so that we can consistently impose our constraints on states. And this is not a very manageable problem. In simple cases it is simple, but in general a general framework is needed. And this general framework is provided by this BFV formulation, because now we know what to do. We just need to find such a quantization to construct or find h-bar corrections to our omega, because all information about our constraints is now encoded in this BRST, now it's called BRST operator omega, right? And all consistency are contained in only one equation, in this equation. So that's why it is useful to speak this language. So let's see if we can give a physical interpretation to such a system. It turns out that it is quite straightforward, because we already gave physical interpretation to classical BFV system. So we say that observables are just operators such that omega hat f hat is 0, so they are BRST invariant, and f is equivalent to f plus right. In fact, it's even convenient to introduce operator d, which is 1 over h I h bar commutator with omega hat, and to observe that this d squares to 0, so which means that in equivalent, and I forgot to say that we also assume the genuine observable should have Gauss degree 0. In equivalent observables, its cohomology of D in our algebra, right? So this operator D is nilpotent. It's easy to check using Jacobi identity for the graded commutator. So if we apply this thing twice, we get 0. So all our algebra U becomes a homological complex with the differential being D, and we can look at cohomology in degree 0, and these are precisely equivalence classes of observables. So almost like at the classical level, where in equivalent classical observables we have cohomology of Poisson bracket with omega. Of course, this D in the classical limit becomes just classical BRST differential. So this D, let's call it quantum BRST differential. Quantum BRST differential. Okay, but there is additional ingredients, so this is simple, it's almost like in the classical case, but now we have a representation space H. So we can define what are our quantum states. And these are precisely states from our H naught. Let's immediately ask them to have degree 0, which are annihilated by our BRST operator, where rho is our representation, right? So that's how our BRST operator acts on our states. So like this. And in the following, I'm going to drop this rho because it's obvious. If I go with omega hat or any other operator on the state, it means that I act using this representation, right? And usually we just drop it not to waste chalk. Okay, and again equivalent, so state psi is going to be equivalent to psi plus something in the image of omega. Now I dropped rho. Which means that again we are speaking about cohomology. In fact, this equation, it's again a miracle of graded story, that this equation is equivalent to omega hat square equal to 0, right? Because it's a graded commutator, there are two terms, omega times omega, minus certain factor, and this factor is also minus because omega is of degree 1. So it's just twice twice omega squared. So that's why omega is an important operator. It's an important element of our algebra U. And that's why, because we have a representation, rho of omega is also nilpotent. So we are speaking about cohomology. So in equivalent physical states, this is cohomology in degree 0 of our omega hat, strictly speaking, rho of omega hat in our representation space. So again, everything is natural. So we have the mochok. Not so optimistic. May I ask someone to bring chalk from another room? So the following I'll formulate as an exercise. Check that cohomology of omega in H is a module. It's very straightforward. Module over cohomology of D in U. Thank you. So we can compute algebra of inequivalent observables. By the way, it's also important to prove that this is an algebra, that multiplication descends there. So this is an algebra. It's straightforward, and this algebra acts on this module. It is well defined. So we can think that somehow, given a quantum BFV system, somewhere inside it, we have a hidden normal quantum mechanics, which is whose operator algebra is cohomology of D in degree 0, and whose representation space is cohomology of omega in degree 0 again. But a more general statement holds that cohomology in all degrees in the representation space is a module over cohomology of D in our operator algebra U. Okay, very good. So let's give a simple example of a system of this sort. It's again relativistic particle. The simplest possible. Slightly more general examples will come. So classically we have what? We have x mu p mu, right? And we have a constraint p squared plus m squared, right? Our mass shell constraint, where square is taken with respect to Minkowskian metric on our space X. Then we introduce ghost variables. So our omega is just c p squared plus m squared. Then we can form our Hilbert space, which is going to be functions in, well, let's be careful. Well, be careful means don't care for the moment about inner product. So let's just take functions in our, what can I do? Like psi of x and c. So like coordinate representation. So I take functions which depend on x on my coordinates and on ghosts. And momenta, as usually I take in coordinate presentation, I take wave functions to be functions on coordinates only, and I think of p as a momenta. So now my psi depends on x and c. There is a degree, right, because c carries degree 1, so it's naturally a graded space. So generic psi is psi naught of x plus c psi 1 of x, right? And there are no further terms because c squares to 0 because it is Grassmann odd. And now my omega hat, there is nothing to quantize, right? My omega hat is just c. P squared becomes what? Minus box, right? I don't put a h bar explicitly. So this differential operator, right? So this is my omega. So what are my physical states? I ask omega acting on psi equals 0 tells me, and together with the condition that my psi should have degree 0, this term is gone because this term doesn't have degree 0, so only this one. So this gives me that so these are my physical states, right? Of course, this is precisely what we expect. It's this is Klein-Gordon equation, right? Which is interpreted as a condition that our constraint annihilates our quantum state. Of course, we don't really need this BFV technology to discuss such a simple constraint system, to quantize it, etc. But still, it is instructive to make sure that our technology produces the standard result, that nothing strange happens. However, it's also a good, something strange nevertheless happen, because we know that in general we need inner product on our representation space to be able to compute averages, right? So quantum mechanics requires us to have an inner product. Let's see on this example first what happens with inner product. So what is with inner product? What about inner product here? Of course, there is a naive one, which is like this. We can mimic the rules of quantum mechanics. We can say that this is just integral over d and x. We are in n dimensions, for instance, dc, right? Because our function is a function of x and c. And then we take psi star of xc, phi of xc, right? This is a good inner product. Moreover, if I'm not mistaken with some, one has to be careful with coefficients. I was not very careful. This omega is Hermitian, right? With this inner product, because box is Hermitian, C is Hermitian, m squared is Hermitian, everything is fine. So everything looks okay. So omega is a Hermitian operator, we have an inner product, everything is good. What worries you about this inner product? Is everything fine?
Maybe non-degenerate.
Well, it's perfectly non-degenerate.
Positive difference.
Pardon?
Positive difference.
No, well, this we give up anyway, because in this graded setup you don't get it.
It depends on C.
What does it mean it depends on C? Well, it's a number, right? If we take a good, like, square integrable functions, put here, it's perfectly defined, complex number. Yes. So first of all, this inner product is of degree -1, because this Bayesian integration over the ghost C takes away 1 unit of the degree, right? So let's do it explicitly. For instance, if we assume such a decomposition for psi and similar decomposition for phi, then it is just integral dnx of something like psi 0 star phi 1 plus, well, of course, maybe numbers are not correct, psi 1 star phi naught, right? So it's like off diagonal, you see? It couples psi 0 to phi 1 and the other way around. So it does not induce a physical inner product on physical states, but this is fine because we know that physical inner product for relativistic particle is a separate issue, and anyway, even if it was 0, 0 here, it's not a right answer because you know what is a right answer. The simplest way is to go to momentary representation and integrate over the mass shell hyperboloid, right? That's what is going to give a Lorentz invariant proper physical product. But this is a naive one. It's non-degenerate, but it carries a wrong degree. And in fact, it's not for nothing that it carries a wrong degree. But still, it's not completely unnatural because what you can do with this inner product, instead of anyway, relativistic quantum mechanics is not a very good physical theory because it should be interpreted in terms of QFT physically, but still, as a field theoretical object, it's completely perfect because if you write the following expression psi omega hat psi, what we are going to get is integral dnx psi naught of x minus box plus m squared psi naught of x, which is a Klein-Gordon action. So this inner product is not far from being wrong in the sense that it gives a right Lagrangian, right action functional for our equation. So it is correct in the sense that in the sense of different interpretation of this quantum mechanics, not in terms of a quantum mechanics, but in terms of a classical field theory of a free fields. And that's probably another possibility to correctly interpret relativistic quantum mechanics. Okay, so what is, let's now get back to general discussion, inner products. So we see that depending on what's going on, inner product can be of degree, of a wrong degree. By shifting the degree in the representation space, we can always assume that the degree of inner product is either 0 or -1. This is convenient not to consider other options. But in order to avoid half integer degree of inner product, of half integer degree in representation space, we need to allow for this possibility. This is actually the reason why sometimes people do it differently. They say, okay, we do have inner product of degree 0, but then our degree is shifted by 1/2, for instance, in this example. But we don't do it. We prefer to keep a degree integer in representation space, but to allow inner product to be either of degree 0 or degree -1. This can always be achieved, no matter what happens. Okay, good. Now let's go to the following discussion. So irreducible representations. Of this omega hat squares to 0. So you can think of this as a one-dimensional algebra consisting of one element which squares to 0, but because we are living in a graded world, by irreducible representations we mean a graded space where omega act and where we can choose a basis of homogeneous of elements of certain degree. So it's, although the algebra is one-dimensional, still it has a non-trivial representation theory. And I ignore all possible difficulties related to infinite dimensionality, because this will take us to different directions. So effectively, I will be thinking of our representation space as if it was, were finite dimensional. And under these conditions, it's very easy to describe possible irreducible representations of omega. And these are like building blocks, because if we have omega, we can then decompose our representation space into these irreducible representations and more or less see the structure of it. Of course, it can be very difficult in reality, but at abstract level, just to get an idea of what it looks like, it's possible to do it. So let's study a little bit how our omega act on our representation space. So first of all, there is an image, right? Image of our omega hat, which is a subspace in H, right? Then there is a kernel of omega hat, which is also a subspace in H. And in fact, image is a subspace in the kernel because omega is nilpotent. So if any element in the image, which means that element can be represented as omega hat acting on something, it belongs to the kernel. So image is naturally a subspace in the kernel, right? But the complementary subspace, so if you want our kernel, if you want a decomposition, our kernel of omega equals to image plus something. This something is not canonical, right? Because if we have a space and a subspace, we can always find a complementary subspace, but it's a matter of choice how to pick it. Sometimes you have additional structures to pick it naturally, sometimes you don't. So that's why we say here E, some kind of a subspace of the kernel. So there is a image is a subspace in the kernel, and E is a complementary. So what is this E? What it is isomorphic to? So we decompose kernel into image plus complementary space. This complementary space is isomorphic to something we discussed heavily. Of course. Cohomology in the setup of linear spaces is just this complement. But of course, cohomology is strictly speaking the quotient of this space by this subspace. But if we pick a complementary space, it means that we pick representative in each cohomology class, right? But as a linear space, it is isomorphic to cohomology of omega hat in H, right? And the same story here. The kernel is a subspace in H, but there is apparently no invariant way to find a complementary space, so we have to introduce it. So we pick some basis, we do something. So we say that our H is a kernel plus some complementary space F. Again, it's not canonically defined unless you have some additional structures, but you can pick it. So all in all, we have that H is equal to image of omega plus E plus F. And the sum of the first two is just the kernel. Okay, and now, because we agreed to work as if everything were finite dimensional, let's pick an adapted basis and see how omega acts in in this basis. So let's first pick vectors G alpha such that their linear span is image of omega. What does it mean? It means that there exist vectors F alpha such that omega hat on F alpha is G alpha, right? That's exactly what it means, that F alpha, that G alpha is in the image. It means that they can be represented as omega acting on something. And let's denote this something by F alpha. And this F alpha, of course, is not unique, right? We can add anything from the kernel of omega to this F. Once we pick such a basis, we can say that, okay, our F is just a linear span of F alpha. But what it looks like heavily depends on our choice of F. Had we chosen different F alphas, for instance, by adding something from the kernel, we would have ended up with different F, right? And then there are some elements, and let's pick a basis in E. So EI, such that the linear span is E, and this is of course just a basis in cosmology. And here we know that of course by definition, because E is a part of the kernel, omega EI equals 0. So that's what we have. So we found a special basis where omega act in such a special form, right? This is of course a standard basis for an nilpotent matrix. Sometimes F alpha G alpha are called contractible pairs because they are like related by omega. And in turn, this is related to this contraction in topology historically. It's like different language for the same. And this is a basis in cosmology. Of course, we can safely assume that all these vectors have definite degree, so it's a basis compatible with the degree. So what we found irreducible representations of our BRST algebra, right? And there are two. There are, let's say, singlets, it's physics terminology, singlets, which is just one-dimensional space generated by, say, E1, and null doublets. For some reason, that's historical terminology. It's a space generated by F1 and G1, right? And omega acts trivially here because it's in the image, and omega on F1 gives G1. So it's like a reducible representation of these commutation relations. So it's quite poor. The theory is quite poor. There are only two distinct representations irreducible, one-dimensional and two-dimensional. That's it, right? Nothing else. So we can decompose any representation space under the conditions which we discussed into a direct sum of such representations. But of course, this decomposition means that we explicitly extracted cosmology, these are singlets, and all the rest which doesn't contribute to cosmology, which are these null doublets or contractible pairs. There are different names for these objects. Okay. The discussion becomes a little bit more involved when we assume that there is an inner product. So what we are interested in next are pseudo-unitary irreducible representations of this omega squared to 0. Then there are more choices. So let me list these choices and make it into an exercise. It's an exercise in linear algebra, nothing difficult, but a little bit boring, perhaps. So there are possible, because you see, it's a little bit involved, because we need to consider two situations where where inner product is of degree 0 and when inner product is of degree 1, minus 1. And pseudo-unitary means that we want our reducible representations to be, so omega is going to be Hermitian with respect to inner product, and inner product is non-degenerate on our representation. So we want to find all possible representations of this type, and there are 4 classes. So first is again singlets. It's essentially the same. It's a linear span of a single vector. Ghost of E must be 0. Of course, omega on E is 0. And this only exists if only k equals 0. K is this. Better even minus k. K is a Gauss degree of the inner product. So these guys exist only if inner product is of degree 0. Unfortunately, there are 2 distinct cases, k equals 0 and k equal 1. So these are so-called singlets. These are, of course, cohomology, because E cannot be omega on something, otherwise it's not an irreducible representation. So it's clearly one-dimensional cohomology subspace. And in addition, because we want pseudo-unitary, we want our E with an inner product. Clash of conventions, because I use it as a linear span. Let's put H here is 1. Right? So we get, indeed, it's a one-dimensional space with non-degenerate inner product, and it's cohomology. So these are so-called singlets. Okay, second thing is doublets. It's some historical terminology, but I don't know what is the best one. What is a better one? So doublets, it's as a term suggests, it's going to be 2-dimensional. So there are 2 elements, E prime, 2 basis elements, E prime. So omega on E is 0. Omega on E prime is also 0. So it's again cohomology. And E prime is 1. The only non-vanishing inner product is like this. The next one is so-called null doublets. So for this, just one moment. For this, we need k equal 1. Because if k equals 0, let me remember, you can decompose it into a sum of singlets. So it is only in this situation it is non-trivial. And then we have null doublets. Null doublets, it's the following thing. We have f g such that omega f is g. Of course, it's clear that g is in the kernel of omega. And I forgot to put hat. And the inner product is like this. F G is 1. Again, K should be of degree 1. Because you see, because omega on F gives G, the difference in Gauss degree is 1. In order to produce something non-vanishing, we need a Gauss degree of inner product to be 1. And finally, the most interesting one is so-called quartets. That's what really we meet them in many situations, including string theory. It even has a name of quartet mechanism, how the degrees of freedom are found in the quantized string. So this is like this. So we have F prime, G prime, hence the name. So there are 4 linearly independent vectors. So omega F equals to G, omega F prime equals to G prime, and the inner product is like this. F with G prime is 1, and F prime with G is also 1. And this happens for K equals 0, if I am not mistaken. Yes. Yes. So let me see. So for instance, let's give a particular example. So for instance, Gauss degree of F is 0, then G is 1. In order, G prime should be also 1, right? So no. So let's example of a quartet, just to be more concrete. So for instance, Gauss of F is 0, then Gauss of G is 1, and G should couple to F prime non-trivially, so it means that Gauss of F prime is -1, and Gauss of G prime is 0. Yeah, that's an example. So you see, so here we have 0 degree, it's correct. We produce G of degree 1. Here we have degree -1, and we produce something of degree 0. And indeed there can be, and the non-trivial inner products, the non-vanishing inner products. So F is of degree 0, G is of degree 0, it's okay. F prime is of degree -1, G, no, sorry, F prime -1, and G of degree 1, yes, -1, 1, can be non-trivial inner product because K is equal 0, so it's an inner product of degree 0. Yeah, that's what it looks like. And this is quite often, these objects, these pieces in the, let's say, in representation space, they quite often appear in applications when we discuss like quantized relativistic particles on strings. In fact, I made one mistake, I have to confess. You can also form, I should remove this. You can also form quartets even if degree of inner product is -1. It's still possible to adjust numbers and to get this. Another subtlety which I was a bit sloppy about is that it might be sometimes you need to put minus somewhere to make sure that omega is really Hermitian, not anti-Hermitian. I don't remember by heart all, and I can't do it immediately. But anyway, it's an exercise. So if you try to find possible these irreducible representations, like minimal subspaces which are invariant under the action of omega and which are compatible with the degree, so they decompose into homogeneous pieces, you will find all these possible irreducible representations. It's kind of purely technical. It's at the level of, it's a linear algebra, but of course you need to remember about degree because it's a graded linear algebra. Okay.
Why do we demand omega to be Hermitian? I mean, it's not observable.
Because we want pseudo-unitary.
So we just impose it by hand.
Yes. Because well, of course we impose it because we want, at classical level, we want omega to be what? Real, right? Everything should be real. And when we speak about quantum systems, we want everything to be complex, right? But objects which were real classical are going to be Hermitian. Strictly speaking, it's better to work with anti-Hermitian, but it is purely technical question. You can always multiply by imaginary unit. But I think there is a better answer to your question. If we want our, yeah, that's a good point. Let's discuss evolution, indeed. Let's discuss evolution. So usually we have, if we have a Hamiltonian, right, we have a evolution. And here, something like this, right? So this defines the evolution of our state psi. But now we want our evolution to be, our quantum evolution to be compatible with gauge invariance, which means compatible with BRST operator. So it means that the evolution should be well defined on equivalence classes. And in particular, this implies that evolution is well defined in cohomology, because our physical states are cohomology of our BRST operator in the space, in the representation space. So let's check that everything is fine. So suppose that at initial moment omega hat psi equals 0. So let's make sure that it's going to stay with the evolution. Is it clear? So so if we go with omega on both sides of this equation, we get omega h hat psi, but because they commute, it is h hat omega psi, and it is 0. At initial moment it was 0, so in evolution it is preserved. In other words, if we start with a representative of cohomology, it evolves to a representative of, the evolution is well defined on equivalence classes, so we can actually discuss evolution in cohomology. What it has to do with why do we want omega? That was the question. Yeah, that's why why we want Hamiltonian Hermitian. It's clear, right? It's the same as in usual quantum mechanics. But why do we want omega to be Hermitian?
Maybe for the same reason.
So we want our we want our inner product. Yeah, let's also do it into exercise. So if we have an inner product, right? If we have H on which we have inner product, then inner product induces inner product on cohomology. Right? So what is the idea? You define inner product to be an inner product of representatives and prove that it does not depend on the choice of representative. So I define this product of equivalence classes of phi psi, right? Cohomology classes, by simply taking this. And I want to be sure that this does not depend on the choice of representative. Choice of representative means that I add to phi something like omega acting on something, but then I need to move it to another to another argument. For this I need to be Hermitian or anti-Hermitian, doesn't matter. Yeah, it's one of the explanations. So we want inner product to be induced on the physical states, which means in cohomology of omega, and for this omega must be Hermitian. Yeah, that's probably a proper explanation. Okay, I have a couple of minutes, so let me give one example of doublets. So it's same relativistic particle. Let's see. So suppose our H is functions in C times, which is just two-dimensional space, right? Because ghost C is fermionic, times some, let's say, V, which is a degree 0 non-graded Hilbert space. You can think of this as square integrable functions on our space-time. Okay, and then let me recall you that our omega is what? Is C times certain operator, let me call it K. It is like box, I don't want to be, so K in our case is minus box plus m squared. But what I want is that, I decompose V into, so in K is self-adjoint, K is Hermitian operator, so I want V to be a direct sum of kernel of K let me think. No, it's not. It's a bit too. Let's be. Yeah, sorry, I'm a bit confused. I thought I remember it, but but I can't. I can't remember it. So, but the idea is very simple. So, okay, let's leave it as an exercise. So let's case K is just an operator in V, because I'm not sure I can immediately reproduce the required thing, and let's K dagger is K. So it's Hermitian. So the question is, so let's leave it as an exercise. It's better than I will take time thinking in front of blackboard because I forgot something. So that's the simplest setup. So we have just one ghost, one constraint, and this constraint is Hermitian. And so the question is to decompose explicitly this guy into reducible representations. Decompose into irreps, which we discussed. But in this case, there is an inner product, which is integral dc times inner product in V. So what happens if you do this decomposition, you will see that in general you have doublets and null doublets. That's how these are precisely the representations which appear in the case of such a simple omega, for instance, in the case of relativistic particle. If we consider, I hope we will have time to do it later in this course, if we consider, for instance, BRST operator for spinning relativistic particles, then we also get doublets, and the same for the strings. But this is the simplest possible illustration, and it's very simple, but I'm just don't want to think in front of blackboard because I forgot some details. Okay, thank you very much. I think we are done for today, and we have offline lecture on Friday. And next week, to tell the truth, I don't want to show up in person here, so maybe switch back to online format. I doubt if I manage to come on next week, I will tell you, but by default I don't. Okay, thank you.